Okay folks, welcome back to part 2 here, and let's look at a couple more examples on that week 10 written assignment. And I'm going to go to page 3 now. So part 3, the title here is Building Models. And in particular, I want to jump ahead to number 3, which gives you an example where it's a type of problem that's a little bit tougher than the examples we looked at before, because not only do you need to set up, put the information into a model and then solve an equation by taking a logarithm of both sides, but you need to build the model from information to start with. So this one says the half-life of radioactive potassium is 1.3 billion years. Develop a model for the amount of a 2-ounce sample that remains after T years. So here's an example where we've got decay rather than growth, but you can still use that basic model. The ending amount's the initial amount times e to the kt, and the only thing that's weird about the decay situation is k, the continuous rate of increase or decrease. This will be negative in this case because I've got a decrease of a certain percent per year. We have to work out what that is, however, and the information we have is that radioactive potassium has a half-life of 1.3 billion years. So let me try to put this into this model. A half-life means that if I started with, say, 1 gram, I'd wind up with half a gram after 1 half-life. So I'm going to put in 1 as my initial amount, 0.5 as the ending amount, e raised to the k here I don't know. I don't know the rate of decrease yet as a percent rate, but I know that the time is the half-life, and this was 1.3 billion years. You know, I could do this in billions, but I'm going to go ahead and write out $1.3 billion with all the zeros, okay? And then I've got not quite all of my model because I don't have the k. I'm going to have to solve an exponential equation to find k, and then I'll have the model that I could use to work on other problems. So let's go through this one, and let's see. I don't have to worry about this 1, so I'll lose that. And here I can take a log of both sides to bring k down out of the exponent. But there's a good choice. Rather than using log base 10, I definitely want to use a natural logarithm here because that's log base e and it plays well with expressions that have e in them. In my next step, I'm going to have the ln of 0.5 on this side. I'm going to keep my color coding a little more reasonable. And on this side, I'm going to pull that 1.3 billion times k, reversing the order, but pull that down out of the from the exponent inside the logarithm to a multiplier out front, and then I just got natural logarithm of e here, right, multiplied by the natural logarithm of e. And this is the part that's really cool. What's the natural logarithm of e? That's the power you'd have to raise e to if you wanted the result e. So the natural logarithm of e is 1, and this is just all this stuff multiplied by 1. So I really like using a natural logarithm with these expressions that have e in them because chances are things are going to simplify much easier. And I can solve for k just by dividing both sides by the enormous number of 1.3 billion. And what kind of number am I going to get for k? A small one, I think. Natural logarithm of 0.5 divided by all those zeros. I get negative 5.3 times 10 to the 10th power, negative 10th power. So let's see, I think I'll give you one more decimal place. So k could be written in scientific notation like this, or move the decimal place 10 times. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, 5, 3, 3. So this will be the value of k if you write it without scientific notation. Kind of clunky, but that'll set you up with a model. And now that you have the model, and your answer should actually look like this, the model should be starting amount or ending amount equals starting amount times e to the k, 2, 3, 4, 5, 6, 7, 8, 9, 5, 3, 3, t. This gives you a general model that you could use for analyzing situations with radioactive potassium. You know, a question about like, you know, how long does it take for only 1/10 of the potassium to be left? Put in a 1 here and a 0.1 here. Or how long does it take a 2-gram sample to decay to 1/10 of a gram? You put in 2 here and 1/10 here and you solve an exponential equation. So these are the tougher problems. You have a variety of them where you're going to use this basic general exponential model and plug in the information you've got and then solve an exponential equation in order to come up with the constant that goes in the model. And then in many of the problems, part B, you have to use the model to do something. Let me go on to the last page where you develop an exponential model and a logarithmic, not a logarithmic, a logistic model based on data. So you've got this table that shows how many kids came down with a virus at an elementary school after how many days. And you're going to find that old sheet. Is it a green colored sheet? I don't know if I made it green for you guys, but if you download that sheet we use for linear models, it's linear and other models from data. It's exactly the same steps. You put the time into L1, the population of infected kids into L2, and this time you select, it's the second menu, second stat, calc, but you choose exponential regression instead of linear regression, and you'll come up with an exponential model. And then part 2 says rewrite this model in the form we've been working with. So let me keep the model up here and just clue you in about that step. The calculator will give you a model that's kind of in this form, where this is still the initial amount, but it'll give you a base here other than E. So for instance, the calculator might say that the population of kids who have the virus is equal to, it'll give you a starting amount, I'm making this up, 2.4, and then it'll give you a base like 1.7 raised to the t, where t is in days. So you get this, but then the next step says, can I write it in this form, using this form, which has the advantage of telling you right here what the continuous growth or decay rate is. So basically, this is the same form. This A naught is the 2.4, that stays the same. But this is the e to the kt right here. And basically, you can see this as e to the k raised to the t. It's the e to the k that's standing in, we want in place of this base. So all you have to do here is solve e to the k equals whatever base the calculator gives you. So don't copy down the 1.7, that'll be different. It'll be whatever the calculator gives you from the exponential regression. But once you get there, then just set e to the k equal to that base. Take an ln of both sides and you'll get k equals ln of that. And that'll give you the k that goes in here, and it'll also give you the growth rate. It'll tell you per day, daily, how fast this infection is spreading among the kids. Other stuff on this page, the third and fourth item, this is part 4, right, last page, says as the outbreak continues, the growth rate actually tails off. So in the initial run, you've got a scatter plot that looks like this, and it works well to fit an exponential model to that curve and find that growth rate. But as time continues, realistic in the real world, you get some leveling off. And a logistic model is basically for populations that initially grow kind of exponentially, but then encounter some kind of limiting factor. This is typical of biological populations in general, right? They tend to grow exponentially until they, you're limited by food or space or some other factors. And the logistic model will kind of level out and actually have a horizontal asymptote above which it does not climb. And there's an earlier problem on, I think, page 3, or maybe it's page 2, where you'll explore the logistic model and see how you can see the value of that asymptote pretty easily from the equation. So here you're going to do it by putting some extra data points into the calculator, going to stat, calc, logistic regression, and finding the logistic model for this curve, which you could also graph like this, and then finding what the carrying capacity, or kind of that asymptote is, which will answer this last question about use your model to estimate the total number of children who will eventually catch this cold. It's kind of a maximum it approaches. Okay, have fun with this, and I will, I think in this case I will eventually send you a key for this assignment, but I'd like you to have your best shot at it and turn it in to me first. And I think this will set you up very well for the homework that's due on Friday night and Tuesday before the final exam. See you later.